I have given you some presentation as well, so you can refer that later. Okay. This one, just 1 second. Let me see. Okay, yes. So today we'll be discussing the artificial neural network. Okay, how artificial neural network is being used in uh, machine learning. Okay, so neural networks is a technique which mimics the human nervous system that we know. Okay, and in the nervous, though I'm not very good in biology, however, the nervous system consists of two things, right? One is that neuron, and there are some connections to the neurons, right? They call dendrites or something like that, dendrons or something. Okay, and in artificial neural network, these neurons are referred as nodes, and they are nothing but a simple computational node, okay, or machine, a simple computational machine. Okay, and these neuron dendrons or dendrites, whatever it is, they are the simple connections, and there will be some weight associated with these connections. Okay, maybe you can think of that some connection may be very close, some connection may be a bit apart from one neuron to another one. Okay, and each input into the neuron has its own weight associated with its illustrated, the red circle. Here it is. A weight is simply a floating point number, that is a real number, and are adjusted, tuned during the training of the network. It's a very simple one. Anyway, I will go to my notes so that it would be easy for me to explain. Just 1 second. I close this. What happened? Yes, it is there. Okay, I come to my notes. I hope that you can read it. Can you see this?
Yes, sir.
Okay, very good. So first, I will be I'll try to discuss the perceptron. Okay, which is a neural network model, and perceptron we have already studied, right? That is a how to find a line separating two classes. Now let us assume the two classes are separated linearly. A line can separate two classes, and for that particular data, how to design an artificial neural network. Now, let me explain what the problem is in this case. We have a training data set, right? We have to have a training data set. This is a supervised learning. And now we are familiar with this notation, right? We have got the objects characterized by xn, okay? And xn, the number of characteristics to characterize the data is d, and we have added this dummy variable xn0, right, which is equal to 1. So xn is nothing but a d plus 1 dimensional vector, and yn is the label, right? This is a categorical value, either c1, maybe c2, or if it is a multiple classes, say c1, c2 up to c small c, c number of classes, okay, you can have. So data is distributed over C classes, and each data point is characterized by D plus 1 features. Okay, this is the data set we have for the training sample. Now, this yn, this is a categorical data, right? C1, C2, class 1, class 2, something like that. Now, let us try to represent this class, this yn, in a different representation scheme called one-hot representation. Just you go to the any data mining or pattern recognition book, and there you will find data pre-processing. Okay, data pre-processing, always there will be a chapter, and in that chapter you can find this representation or one-hot representation. Actually, in the data, we may have categorical data, right? Maybe color, gender, right? Name, department. These are actually categorical data. Now, since they are categorical data, say male, female, right? It is we need to convert that to quantify, right, or real value. So here is a way to convert the categorical data in a different manner. Now, say one hot representation is this: we have a column called gender, and gender has got two different values. Right now, let us assume only two. So one is male, another one is female. You know, right? You cannot just add, multiply, you cannot order them, which one is small, which one is big, and you cannot divide them and all those stuff. So how to quantify this data? This is one way to quantify is that you break that particular column into two columns. One is male column, one is female column. And if the person is male, you just put 1 corresponding to the male column and 0 corresponding to the female column. Like YN, and it is a male, right? This candidate is male, C1 is male, then or class 1, if it belongs to class 1, so in this case, class 1 component will be 1, class 2 component will be 0. And that person is female, that is in class 2, then YN value male component of that particular object is 0 and female component is 1. This is one hot representation. That means if you have say C different values, you have to have YN1, YN2 up to YNC, and depending on the class it belongs to, that particular component will be 1, remaining components will be 0. Okay, so one of the C values, YN1, YN2, YN3 up to YNC, one of them will be 1, remaining are 0. Okay, there are a lot of other advantages as well. Okay, anyway, this is called one hot representation. Now, in the artificial neural network, instead of labeling the data like C1, C2, C3, C4, or yes, no, good, bad, what we want to do is that we will be converting this into this one hot representation, and we will make this Y1 as a vector. Okay, so instead of putting Yn equal to C1, we will convert this Yn into a vector of 2 dimensions. If that is in 2 classes, it would be Y. If it belongs to C1, it would be 1, 0, right? And Y2 will be 0, 1. So depending on the values, we can always do it. So now our training data converts to this, right? Xn remain the same, but Yn earlier it was referring to a level, right? Class, in which class it belongs to, either C1 or C2 or CC. Now that we do not want to look at that. Instead, we want to look at that as a one hot representation, right? It is a C component vector. One of them is 1, remaining values are 0. Okay, like this one. So now the training set becomes like this to us. And we can always say Xn belongs to a D plus 1 dimensional real space. We are very much familiar now. And Yn becomes data, a point in the C dimensional real space, right? Say 1, if it belongs to class 1, it would be 1, 0, 0, 0, 0. If it is in Cth class, 0, 0, 0, 0, 1, like that. Okay? So now the training data is something like this. Now, what the ANNs are? ANNs are computing system inspired by biological nervous system, collection of nodes, artificial neurons connected in a particular manner. We come to the architecture. Now, neurons receives a real number as input, that is signal, and provides an output which is a nonlinear function of the sum of the inputs. Okay, that is very simple. As I said, the neurons are some small computing nodes, machine, okay, that receive some input, do some processing, simple processing, and pass it on to the next level. That is the job of the neurons through the connections, right? The dendrons or dendrites, whatever you say. Now, I am just showing first for a simple linearly separable data, okay? And that's why we'll be having only 2 layers of nodes, okay? Now, and assuming the data is linearly separable, then I'll generalize it for non-linearly separable data. So xn is something like this, xn0 up to xnd. Note that xn0 is the bias, and yn, right? yn1, yn2, ync. This is the one-hot representation of the class, because yn is the level, which is categorical data. We transferred that, quantified that, and converted that a c-dimensional vector. All are 0 except 1, 1. Okay, in the class it belongs to. That part will be 1, otherwise it will be 0. A very simple one. This is the architecture of the artificial neural network. This is the architecture of the artificial neural network. The number of nodes, this is the input layer. Okay, and number of nodes in the input layer is equal to the dimension of your input data. Nth data object, you have got xn0, xn1 up to xnd, right? So, and xn0 is biased. So here it will be there, and there are 0, 1, ith, generalized one, ith node, and this is the dth node. So number of nodes in the input layer will be equal to the dimension of your input or your object. Okay, and number of nodes in the output layer will be equal to the number of classes you have. Here, how many classes you have got? C, and here you see 1, 2, 3 up to jth is the generalized one, and cth node here. Okay, and you are feeding the data through this input layer, and nodes in the input layer, this activity is very simple. It receives the input, pass it on. Now this data has to go to the output layer, and each of these output nodes receives input from all the nodes in the input layer. So this node, the first node, will receive input from 0th input node, one first input node, ith input node, and dth input node. 2 also will receive, right, inputs from these input nodes. Jth node also will receive, cth node also receives. I didn't draw all the connections, otherwise it would become very clumsy. I just demonstrated here 1 and j. Okay, jth node, this is the generalized one. That means each node in the output layer, okay, will be connected to all the nodes in the input layer. Note that the nodes in a layer within the itself, right? That means nodes in the input layer are not connected themselves. Nodes in the output layer also not connected themselves. Okay, so nodes of a layer is connected with the sub or the previous nodes of the previous layer, and all the nodes in the previous layer. Okay, so node, right, jth node will receive input from all these nodes in the input layer. And another thing we have said that these connections, right, will have an weight associated with that. Okay, and this node, this connection connecting the 0th input node to first output node, what we have put here as we defined or denote that as W10. One node in the output layer receiving from node in the first node in the input layer, that connection weight will be W11. Okay, likewise here jth output node is connected with the ith input node, and the weight associated here is Wji. Normally we do here, whenever we name something W, the suffixes are, first one is source, second one is destination. But in this particular case, we are doing the other way around. W of destination node, and then the origin or origin node. Okay, origin to destination, but it is in a reverse way, Wji. This is nothing, but you can do it Wij, does not matter. But if you take this notation, your writing program and mathematical computations or expressions will be easy to remember. That's why we have done it. Here, instead of putting it as Wij, normally source to destination, we do it in different way, destination first and then source, Wji. So Wji is the weight associated with the connection connecting ith input node to jth output node. Okay, and this is the one. Now each node in the output layer will receive weighted sum, right? They will receive inputs from all the input nodes, and these input signals will be multiplied with these weights, and there will be some weighted sum, right, in each node. Like in the jth node, right, receiving input from 0th node is xn0, that would be multiplied with wj0. So xn0 into wj0 plus xn1 into wj1, xni into wji, xnd into wjd. So all those weighted sum will be performed or computed at jth node, and then it will do some mapping. It will transfer that value to another domain and provide the output vnj. I have written here. So these are the input layer, these are the weight output layers, and wji, that is the weight associated again with the connection connecting ith input node to jth output node. Okay, and I varies from 0 to d, right? 0 to d, and j varies from 1 to c. These are very important. While writing program, you will realize it. These are very important. And then input to the ith node in input layer is xni. Output of the ith node in input layer is same, xni. So job of this input node is very simple. It receives the input and provides the same output. Input nodes are very simple. Now input to the jth node, as I said, in the output layer, that is xn0, wn1, xn0, xn1, xnd. Actually, this will be x, multiplied with the weights wj0, wj1, wjd, as we have seen, as we have said. And suppose the total weighted sum, we refer that or denote that as unj. That means nth data point we are feeding, and unj in the jth node, what is the total input? That is xni into wji. As I said, right here, if you go xn0, wj0, xn1, wj1, xni, wji, xnd, wjd, as I said, and that is true for all j equal to 1 to c. Okay, so we calculate the total input, okay, accumulated input in the jth node, and then output of the jth node will be, as I said, there is a function, right, we use in the output layer, and that function argument will be this sum. So vnj is the output of the jth node, like vnj. See, vn1 is the output of first output node, vn2 is the output of the second, vnj is the output of the jth node, vnc is the output of the cth node. So vnj will be phi, some function of unj. Now what this function is, this is a very important one. Actually, this function which maps a value between minus infinity to infinity, because this unj can be anything, because there is no restriction on this xni, right? The input feature can be, value can be anything. And weights also, I didn't put any restriction. They are some real number, that's I said. So this value, weighted sum, can be anything between minus infinity to infinity, right? So phi is a mapping. This is a function that maps a value between minus infinity to 0 to 1. Note that this is a closed interval, like in logistic regression we say. It can be 0, it can be 0.1, it can be 0.11, it can be 0.5, anything between 0 to 1. That's how we are doing. Okay. Now, what is the reason, right? Why are we doing it? Obviously, this phi, we can bring in some nonlinearity into the system. But as I said, we are working on to find a line, right? A separator, which is a line or a plane, a linear function. Then why shall we go for it? One major reason, what I feel, is that we are going to compare the output with our expected output, right? Or target output. What are these values? These values are either 0 or 1. Either 0 or 1. Now, if I try to compare 0, a value which is in between minus infinity to infinity with 0, 1, right? That does not look good. Instead, we can give some mapping, right? That, okay, we'll map these values within 0, 1. We can do it. And it is not necessarily that it is what I'm saying, that it is closed interval 0 to 1, right? So it can be either 0 or 1 as well. So you can use simple delta function. That means you can put some threshold. Okay, if the value is, say, less than or equal to some constant 0 or maybe a, we can consider that value as 0, or it is 1, or you can take any value, right? Now, if you be flexible, I think it is better to have any value between 0 to 1 instead of transferring those values or mapping those values either to black and white 0, 1. Okay, you can do it, but in general, what we have seen, that does not work well for complex problems. Okay, now what this function is, and that is the sigmoidal function, right? All of us know is a very popular one. The form of the function is this. Okay, earlier case we didn't put this a. Actually, it is same as e to the power ax by 1 plus e to the power ax. Same function, right? So this is the function we use, and this is the sigmoidal function, and it has got lot of advantages. So if time permits, I'll tell you later. And note that this capital A is greater than 0. And depending on the value of A, the form of the function is different. Okay, the inclination of the curve will be different. And this is a very important parameter when you execute MLP. In fact, I have suffered a lot. I had to spend 15 days to find the problem for one real life problem which I was trying to solve it sometime in 2012, 7-8 years back. Then I just considered the actual value or the ideal value of A, and we got the solution. So this is a mapping. Now again, I have written here, this is our training data. UNJ, the accumulated weight or accumulated signal to the jth output node is summation xni wji I equal to 0 to d. VNJ is simple mapping, right, of this UNJ to 0 to 1, that is phi of UNJ, j equal to 1 to c, and this phi x is this function. Okay, now at the jth node, what is our expected value? That is YNJ, right? Either 0 or 1 with something, we know that. And then VNJ is our obtained output, VNJ. Now, what is the error? It would be YNJ minus VNJ square. Okay, square error we have calculated. And then how many J you have? You have got C nodes, right, in the output layer, J equal to 1 to C. So you sum them up, this is the square error, right? What we have calculated for J, C number of classes. And together with that, we have just added one constant here, half. Okay? See, it doesn't matter, you may not do that, but if you add this or this half, right, it would be convenient for us in future. That's why we have done it. There is no mandatory reason, okay, or it is not mandatory to add this half. But if you add this half, then it would be convenient later. When we differentiate these two will come so that we can cancel out. That is the only reason. Okay. Another thing is that you can always put VNJ minus YNJ whole square also. So here also what I have written here is target minus estimated, not the other way around. Because while differentiation, this minus will come, and that will be helpful for us to remember the formula. That's it. Okay, you can do it other way around, but then you have to be careful while doing the further calculation. So it is better to remember this one. We'll write down YNJ target minus estimated whole square. Okay, and for how many n we'll get? The number of data points, right? How many data points we got? Capital N, because we'll fit the first data point, we'll calculate E1. Then second data point, calculate E2. Nth data point, calculate En that way. Now, what is the total sum of square error? That is SSE. That is, you sum them up, right? E1, E2 up to En. Then what is the average SSE? You just divide that total SSE by n, right? This is what. So this is nothing but this En. Now let us see what this En is. En is nothing but this, right? En is nothing but half into summation Ynj minus Vnj. These Ynjs are fixed, we cannot change. Vnj, something we have calculated, right? Now what is Vnj? That is a function of Unj. This is simple mapping. Don't worry, that is also not an issue. Now what is Unj? Unj is a function of Xni and Wji, right? So all the input values as well as the weights associated with the connections, right? We have introduced. Now you see Xni, those are the values, right? That objects, feature values of all the objects. That also we cannot change. That is our training sample given to us. Only thing we have in our hand is Wji, which are so far unknown, because Wji, something we have introduced in this particular neural network and which we have in our hand. Xni's, no, we are given. Wij's, we are given. Sorry, Ynj's are given to us. Only thing we have introduced here are these Wij's. So what we can say is that to us, this En, the error, whatever we calculated, that is function of Wji's. So objective now is to find Wji, right? That would minimize this error. Okay, so like in regression, right? We have calculated the error, which are function of those parameters, right? A, B, W0, W1 up to WD, whatever it is you say. So this is function of Wji, and we can just modify that. We cannot modify the data value, right? As well as the level of it. So our objective now to find these W's that would help us to minimize this error. And when the error is minimized and the minimum value of this error is 0, when all the data points, all the training samples are perfectly classified in the respective classes, right? And that's what we want to do it. Another way to think of, since this is a sum of square error, and each error, right, error for each data point is a square. This is always positive. Now we can always say that this error, capital E, the average error, will be minimum when each En is minimum. Now error for each point is minimum, right? Data point is minimum means E will be minimum, and vice versa. So minimizing capital E is equivalent to minimizing all the respective ENs. I guess you will agree with me. If you have any doubt, we can discuss later. Okay, so instead of minimizing capital E, we prefer to minimize En, but there is nothing wrong if you try to minimize capital E in one source like we have done in regression. Okay, but there are some drawbacks as well, and there will be a lot of questions in your mind that why are we not trying to minimize this the way we have done in logistic regression, in regression. Now question is, yes, you can do it. You can always differentiate this function with respect to Wji's, and you can find out, say, linear simultaneous equations, right? You can do it. Now think about a problem where you may have a data set, say maybe 100-dimensional data. Okay, so here you will have 1, 0, 1 input nodes, and maybe there are, say, 10. Okay, they are belonging to 10 classes. So how many connections you will have? That is 1, 0, 1 into 10, right? So if you have, say, here D plus 1, you have C classes. So number of weights will be D plus 1 into C. It's a huge. But in the regression, normally we consider regression or something which are very simple. Now think about a set of simultaneous equations having 1, 0, 1, 0 parameters and 1, 0, 1, 0, 1010, right? Equations with 1010 unknowns. And obviously, you may have some issues. You may have some issues to deal with such a huge matrix. Okay? Now, to avoid that, can we come up with some approximation technique that would help us to find optimum value of W? Okay? And to come up with the rescue, Rosenblatt has given us the back propagation technique. Okay? That means we'll calculate the weight, then we back propagate the weight and modify these weights. Okay? Iteratively. And in numerical methods, in mathematics, very well-known technique is available, that is gradient descent technique. Okay, and gradient descent technique we will apply here, okay, to find the optimum value of weight. And as Swarup was saying, that why don't we use deterministic technique? Yes, we can. You see, only this is the only two layer, right? Simple neural network model. And here to model that, if you have say 100 features to characterize objects and there are belonging to 10 classes, you will have 1000 more than 1000 parameters, right? So you have to solve more than 1000 equations. Now, if you see in the current age of deep neural network or deep learning, where you will have, if not billions of such parameters, there will be millions of parameters in CNN. When you say work for say face recognition or many other character recognition, yesterday somebody was telling, right, that sentiment analysis and all those things, there you will have billions of parameters. And it is not possible, in fact, to solve billion simultaneous linear equations of billion parameters. Okay, the machine cannot handle that. That's why we will be using some approximation technique to find out the optimum value of these weights. Okay, I hope I could able to make it clear. So if you have any doubt, we can discuss again later about this, that why instead of going for a deterministic method of finding this optimum set of weights, why shall we go for this approximation technique? But as I said, that we can always go for deterministic if you have a limited number of parameters, right, in your model. You can always go for it, but I prefer that. Okay. Sorry. So here we will be using technique, gradient descent technique given by Rosenblatt, okay, in 1970s or maybe in early 1980s, long back, almost more than 40 years back. He has given the technique following Newton's gradient descent, right, more than 200 years back. So how many? 3 years? 400 years. 1690, right? 1700. So 400 years, yes. So that technique is being used and it is very, very proven, authentic technique, no use of it. But before I explain that particular technique, let me explain you what the algorithm here it is. Okay, algorithm or training this particular neural network model is this. You randomly initialize WJIs and there will be eta, okay, with this gradient descent, that is eta, a constant. You can be 0.01 or 0.1 is quite high value in this case, 0.05 or 0.01 is okay. And there will be some epsilon, right, when to stop the algorithm. If the error value or the average error is less than EPS value, we stop it. Or maybe you can do that number of iterations, right? You decide that, okay, you will execute that 1000 iteration or maybe 1 million iteration, that you decide. Instead, you can decide some error if the training error, right, is less than some value epsilon, and then you stop it. You do not want 0. But anyway, and then you repeat for each data point n equal to 1 to capital N. You just put capital E equal to 0 and then we'll calculate the error. You calculate UNJ, nth data we know how to calculate UNJ, that is summation xni wji, I equal to 0 to d. Then once you get the UNJ, then you calculate VNJ. You can assume A equal to 1 in the beginning. We know, right? VNJ is equal to phi of UNJ, and we know phi 1 by 1 plus e to the power minus x. And then you calculate En, we know, right? Summation Ynj minus Vnj whole square, and there is a half in the beginning. So we can calculate the error for the nth data point, and then we use this technique. This is the gradient descent formula. I'll explain that below. You just take it from me. Wji equal to Wji minus eta into del En del Wji. We are reducing En. Okay, then you calculate En. I have written here by mistake. It should be at the top. Anyway, modify Wji using this. Okay, this is the formula. Now, obviously, within the program, you cannot differentiate, right? So we have to find out something, what this expression is. I will do that. That is the backpropagation. Rosenblatt has given it, and we can do it. It is very easy. Once you come out of this, then you total error, right? What we have done is, and this should be inside actually. Okay, this should be within this bracket. For each error, you add this ENO after coming. Anyway, you calculate, take the total error, right? And then you just repeat this unless this E is less than epsilon. Yes, En we have calculated. Oh, this one should be out of this loop. This E equal to 0 should be out of this, because we are accumulating error for all the data point and putting here. So it should be out of this here. Repeat and then E equal to 0 and then go for it. Okay, sorry about this. And then until E, right? Within the iteration, the total error is less than epsilon. Once it is, then you stop it. Okay. Note that, as I said, our objective is to minimize capital E, that is sum of error for all the data points. Now, what we are doing, we are calculating for the error for one data point, and immediately we are backpropagating it, right? And as I said, that since the error function is, this function is very nice function, is a square, positive, right? Greater than equal to 0. Greater than equal to 0 for all n. Since that is the function, that's why minimizing capital E is same as minimizing all the ENs. Okay? And there is another advantage of this also. We'll discuss this. Now, this particular technique, instead of minimizing capital E, this total error in one shot, since we are minimizing each En, this particular technique is not called gradient descent. It is gradient descent, but there is another name for it, stochastic gradient descent. Okay? Sometimes in some of the problem, we do not use all the training samples, okay, to perform or to modify the weight in each iteration. Suppose you have, say, 1 million data point to train. You run this maybe 1,000 iteration, and in each iteration, instead of considering all the points to train this one, you just use a subset of them to train it. Randomly, you select maybe 10,000 in each iteration, and 10,000 points only you use to modify the weight. Then you go for the second iteration, you would use another set of 10,000 points like that. Instead of considering all the points in an iteration to train, you can select randomly a subset of points and do that. Okay, there is another technique and we follow that. However, if we calculate total error and then modify this weight, then it is called gradient descent. But since we are doing it for each point, it is called stochastic gradient descent. It has got advantages also. If you are interested, we can discuss it later. Okay. It can avoid actually small hinges of local minimas. There is a very good advantages. And another one, as I said, that instead of using all the points, right, in each iteration, we can select a subset of points to train the system in each iteration. Over all the iteration, when you complete it, maybe all the points will participate in training, but not in every iteration. So this is the algorithm you use to train. Now, once that error is you are satisfied, you get a set of W, right? Now, once you get a set of W, that's what we are discussing. Once you, then the training is completed, right? Now, for the unknown data, we feed it, same W will be used to predict that VNJ values, whatever you got, right? And that VNJ will be the class. VNJs will be either, it will not be 0 or 1 exactly, but if the values will be in between something, right? Something between 0 to 1. Some values will be maybe 0.001, another point will be maybe 0.000.1, another value maybe 0.9, another value may be something like that 0.00003. Now, obviously, right, the 0.9, the value, right, if it is corresponding to jth class, so obviously you will put that particular object into the jth class, right? The maximum of the VNJs will define the class of the object. That is the testing part, or later you can predict that one. Okay, so here minimizing En for all n 1 to n will in turn minimize capital E. This is the gradient descent technique, and I'll just explain that fast, the mathematics of it. Some of you may know, but just for the simplicity, or maybe for completion, I want to explain it, what actually it is. It is a technique we have studied maybe first or second year of our graduation course in numerical methods. Okay, the technique is very simple. Suppose we have a function in 2 dimension. X is the independent variable, y is the dependent variable. This curve is y equal to fx. Now we want to find the minimum. Okay, here is the minima. Where does the minimum value come? Here what we say, first we assume a random value, okay, initial solution, that is x0. Sorry. Then you draw a tangent at this point, and you go in the opposite direction of tangent. You see, when you draw the tangent, what is the direction of tangent? If y equal to fx, then tangent is f dash x0, right? F dash x0 is the value gradient here. So you go in the opposite direction. That's why x0 is the current value, and you go to the opposite direction minus f dash x0. Now, what is the step? You have to jump something, right? That eta is the step. So you multiply this f dash x0 with some constant value, that is 0.1, a small value you take in general, and you multiply that and subtract it. This eta is always constant. Then again at x1, you draw a tangent. The tangent value will be, gradient value will be f dash x1, and new value will be x2 equal to x1 minus eta f dash x0. Now, if you want to find out the maxima, we do here plus. Since we are trying to find out minima, that's why we are doing it minus. So maxima means you go towards the tangent. Minima means you go against, opposite direction of tangent. That's why in the gradient descent, it is minus eta, this formula. If it is gradient ascent, means it provides you the maxima, then we go for plus. Okay, so this is the gradient descent technique. So it is an iterative method. Xn plus 1 will be xn minus eta into f dash xn. This is very simple, and obviously this is an approximation method. Now there are different reasons. I'll talk about this. Issues. What are the issues? Obviously the initial solution. Here I got x0 here. Now unfortunately someone got x0 here. Then obviously the minima C will get here, not this one. Because here if you draw the tangent, and opposite direction of tangent means you will try to find out here. So initial solution, if the initial solution is not proper, you may get stuck in the local minima. So this is a local minima, this is another minima, this is another minima, right? In this curve, you have got 1, 2, 3 minimas, and depending on the initial solution, you may get this one if you are lucky. If you are not so lucky, you may get this, otherwise this one, right? There is a chance. That's why gradient descent technique has an issue to get stuck at the local minima. But there are ways to avoid it. I'll talk about that. And another thing is that how to select this eta. we are jumping, right? Suppose you come here and then you select an eta, it will come somewhere here, then you select, then it will oscillate, right? So you have to select an appropriate value of eta. So if you go for a larger eta, obviously, right, you will, your rate of convergence will be high, you will go very fast towards the minima, but once you reach close to the minima, you will oscillate here from this side, that side, that side. So you may not be able to reach close to the minima. Okay, so larger W eta, it is good, right? It has got advantage that convergence rate will be high, but going or reaching close to the minima, you may have some difficulties, challenges. But if you assume smaller value of eta, that would obviously give you a better result, right? Here it will not jump, right? It will not oscillate, rather you will be able to go reach close to the minimum. But this convergence rate will be slow. Maybe if you have, say, maybe 100 iteration to reach to the minima, then maybe you have to perform 1000 iterations to reach to that. And it is true, right? If you want to find a quality solution, you have to pay more, or any quality product if you want to buy, obviously you have to pay more, isn't it? That we have seen in general. Now you may ask that what is the solution of the first one, right? Local to avoid local minimum. So one of the ways, very easy way, and people follow that, you, instead of executing the program once, right, with one random initialization of W, you execute your program 10 times, and with the expectation that at least in one case you will be able to get an initial value within this range, right? So that you can get the global minimum. Okay, so that is the best way to do that, and that is the way, that is how actually we try to avoid this getting stuck at local minimum. But if you're, as I was trying to say, that if you're that error value, you calculate using cross entropy error, right, maximizing the likelihood, then the function will have only one minima. It is a convex function, means only one minima. Then you do not face this problem. Anyway, now, as I said, right, in the backpropagation technique here, this backpropagation technique, we cannot write program like this, right? Computer does not know how to differentiate a function. Instead, can we simplify that? Yes, we can do it. And where I have tried to explain it very easily here, Wji equal to this. And using the chain rule, we have calculated this one. En, okay, En is equal to, I'm telling you, half into summation Ynj minus Vnj whole square, right? J equal to 0 to A1 to C. Now, if I differentiate that, there will be there will be eta is there, right? This eta is there, minus is there, and there will be a half of this, right? The square, if you differentiate half, half is always there. If you differentiate this, there will be a 2 into Ynj minus Vnj. And differentiate this with respect to Wji, Ynj does not have Wji, only Vnj has Wji. So there will be a minus del Vnj del Wji. Okay? Now, if I differentiate Vnj again with respect to Wji, what is that? The Vnj involves phi Unj, right? Now, you differentiate phi Unj with respect to Wji, it would be phi dash Unj del Unj del Wji. Okay? These two cancelled out, this minus 1 will be here, coming here plus. See, it is a simple one. So phi dash Unj into del Unj del Wji. And what is del Unj del Wji? That is only xni. This is a very simple. You see, all are known to us. We know phi, so we can always calculate phi dash also. Anyway, so actually that is nothing, but you will see that later it would be Vnj minus 1 minus Vnj. But anyway, you can do it. So this is the formula, right? The modified formula for Wji. So you calculate the, you do not need to need En to calculate this, because Wgi we know, eta value we have assumed, Ynj value we know, Vnj value already we have calculated, we know Unj, so we can always calculate phi dash Unj, and xni also know. So you put those values into this expression, you will get a modified WJI. Okay. So come back to this architecture here, right? You see here. So what we are doing here, you feed one data, okay, through this network. It goes through all those things and it provides VNJs. Okay, then you calculate the error. Now you backpropagate this error to modify WJI. That is theoretically in our mind, but while writing program, you just follow this one. Okay, here, very simple. You calculate UNJ, that is summation W, that is summation XNI WJI, VNJ, which is phi of UNJ, and then you just use those UNJ, VNJ, and phi test, right? That function you use to find out the modified WJI. Now, once you find WJI, then you can calculate it. Okay? Just 1 second. These people are coming. I don't know why. Okay. So that is the one technique. Now, this particular method, this is a single layer perceptron, we refer this as, and it has got an issue that it cannot deal with non-linearly separable data. Okay. Now, to find the non-linearly, how to deal with the non-linearly separable data, just 1 second. One second, I'm sorry, I'll take a break here. Sorry about this. Okay, so can you see the presentation now? Sarup?
Yes, sir. It's
Yes, sir.
visible.
We can.
Okay. Now there are some issues with this, and unfortunately, this perceptron, the single layer perceptron, we refer that there is only one layer of weights, and this cannot handle the non-linearly separable data. Now, to handle the non-linearly separable data, we have to have another set of nodes, not one set of nodes, but we can have multiple set of nodes. So we introduce multi-layer perceptron. Okay, and now I'm just trying to explain here the multi-layer perceptron, and then I'll come some mathematical background of this MLP and all those things, and obviously I'll refer in between also. Problem is same, and then obviously we know that ZOR, right? If you write your a perceptron, right, single layer perceptron, artificial neural network, and you just fit 4 points, it will fail to classify those 4 points, right? ZOR data that is not linearly separable. Now in this case, we have to have multi-layer perceptron. It is a simple, the data set is same, classes are also same, only that data is not linearly separable. Okay, so the architecture is something like this. This is our input nodes, input layer. This is the output layer. Input nodes, number of nodes are same as the dimension of your input data. number of nodes in the output layer is equal to the number of classes, and then we introduce another set of nodes in between them called hidden layer. It is not necessarily that you have to have only one hidden layer, but you can have multiple hidden layers. Okay, but one proof is there, one theorem is there. If you have single hidden layer, you can separate or you can find the boundary of any non-linearly separable data. So single hidden layer is good enough to separate or find or design a classifier to classify the non-linearly separable data. I am explaining that with a single hidden layer, and then I have already shared one backpropagation technique that would help you to understand the backpropagation technique if you have multiple hidden nodes or hidden layer. Okay, I'm not going in the beginning, but later I would have done actually if it is in the board and all. Maybe it will take another 5 minutes. However, I'm sure that you will be able to understand from this backpropagation technique. And if you do not have any issue, you ask me, I'll explain that again. But here I'll just explain using only hidden layer. Here the thing is same. You just feed this data. Here there will be two sets of weights. One is WJI, another one may be W dash KJ, W and W dash. WJI is the weight associated with the connection connecting ith input node to jth hidden node. W dash KJ is the weight associated with the connection connecting jth hidden node to kth output node. Now, here in the hidden layer, there is one 0th node, right? The bias node, we say. Note that this 0th node does not receive any inputs from the input node. This is same as like bias here. Here also it would be 1 and it will forward 1 itself. Okay, so this one does not receive anything. So UNJ, note that here I have written UNJ is the accumulated weight at the jth hidden node. It would be equal to summation xni into wji, I equal to 0 to d, and this j, right, does not vary from 0 to h, but it is 1 to h. There are h nodes here. Note that. So this 1 to h will receive input from the input nodes, but this one we have introduced for the bias node. Okay, so this j varies from 1 to h. Now what would be the vnj? The same phi nonlinear transformation will give, and these values will be 0 to 1. Okay, and then this u dash nk. Okay, another thing I just forgot. All these nodes, right, will receive or connected with all the input nodes. I have not drawn here. Similarly, here all the nodes receive input from all the nodes in the hidden layer, including this bias. Okay. Now, what is u dash nk? U dash nk is the total accumulated signal at the kth output node. That would be equal to vnj into w dash kj. Okay, this is the weight as a total signal to the kth output node, and v dash nk will be equal to phi of u dash nk. Okay, this phi may be different. How phi may be different? That a value I said, right? That's so depending on a value, you can change it. Here one a value, here another a value. Okay, u dash nk. So we calculate v dash nk. Once you get v dash nk, that is the output for the nth input for the kth output. Similarly, you will receive v dash n1, v dash n2, v dash nc, right? So all these v dash values will be your estimated value in between 0 to 1. So what would be the error? Expected output is ynk and obtained output is v dash nk. So you square that, sum them up. How many nodes in the hidden layer? Output layer, that is c, and multiply that with half. Okay, two things I should have mentioned. What should be the value of h? Number of nodes in the hidden layer. Okay. For your information, in my knowledge, there is no concrete guideline about the number of nodes in the hidden layer so far. Okay, nobody has given any guideline what should be the number of nodes. Now here, that is very interesting stuff. I'll just explain that towards the end of this lecture. Okay, but in general, thumb rule is that H is equal to average of the nodes in the input layer and in the output layer. Okay, so H is equal to D plus C by 2, right? That is the thumb rule. It is the average of the nodes in the hidden layer and in the output layer. However, there is no concrete guideline. Sometimes you may have to increase the value of H, sometimes you may have to decrease the value of H. And both has got some problems, some issues. If you reduce the value of H, obviously computationally it would be faster, but there is a problem that you may not able to achieve a good result. But if you increase the value of H, you may achieve very good training error. That means training error will be 0, but there is a problem for the out of sample error for overfitting. Yesterday, myself and Swarup were discussing about this one. You may encounter overfitting if you increase the number of H. Obviously, this number of H will depend on the number of training samples you have. If you have very large amount of training samples, you may increase H, does not matter, it will work. Okay, but suppose you have got 1,000 training samples. In what I have seen, maybe then you can use here 50 values for H. But if you have say 100, what I suggest maybe you use only 10 or to 5 nodes in the hidden layer. Now, if you increase the number of nodes in the hidden layer, number of parameters, right? This WGI, W-K will increase. In general, the thumb rule of VC dimension, yesterday, first day we were trying to explain. The rule is that if you have the number of data set is capital N, training sample is capital N, the number of total parameters should be N by 10. Okay, or other way around, if you have say D number of parameters, number of training samples should be greater than 10D. You remember, you understand? But so number of parameters should be 1/10 of the total number of training samples. Now, if your number of parameter is more, you have to have you include more training samples. Okay, that then you can avoid overfitting. That is a thumb rule, and I have seen that experimentally it is proven, but not theoretically. But anyway, that is the one. And in this particular case, let me show you how to do this. The algorithm is same. Okay, you initialize this WJI, W-KJ, and then you calculate UNJ, you calculate VNJ, you calculate U-NK, you calculate V-NK, and then you back propagate this error, right? EN into this to modify W-KJ. And first you modify W-KJ and you modify WJI. This particular computation is bit complicated, okay? But anyway, it does not matter. If you just keep yourself cool and calm and just follow the simple mathematical steps, you will be able to reach it. W-KJ minus eta into del En del W-KJ. This part is simple, right? As earlier case, you will have say this half is there, right? Half is there. So differentiate this with W-KJ. W-KJ involved with only V-NK. So it would be 2. All other terms will be 0. 2 into INK minus V-NK and del V-NK del W-KJ. Though there are C terms, but W-KJ involved only with V-NK. V-N1 does not have W-KJ, right? V-N2 does not have. Only V-NK has W-KJ. So only this part. The remaining parts will be 0. Differentiate it, will differentiate them. And just go ahead with this and you will able to reach this one. And this here, delta NK, I am referring as this part. This part, this part is delta NK. And I have sent you that one back propagation derivation or something, right? One separate PDF file. There you will find this very effective or very easily you can understand it. Okay, So we can calculate W dash Kj using this formula. Now, how about Wji? Wji, note that here, right? And obviously this En will depend on Wji also. Now you see Wji provides, helps to calculate Vnj. And this Vnj goes to this Vnj goes to this Vnj goes to this Vnj goes to this. So all these Va dash Nk will have an impact for this Wji. That's why it is a bit longer, or I won't say it is a very complex, but you have to follow it. So you cannot just get rid of this summation in the beginning like here. We got rid of this summation. So here it would be same as half will be cancelled out with the derivative 2, and this minus will make this minus plus. So we got this one, right? Del V dash Nk. Now see, this V dash Nk will have Vji in that, right? U dash Nk. So you differentiate phi dash U dash Nk and del U dash Nk. Now del U dash Nk will have W dash Kj only, because only Vji, right? That will have W dash Kj into del Vnj del Wj. Only Vnj has got Wji. Vn1, Vn2, no other Vn other than Vnj has this one. So only this one, and then we can differentiate this Vnj, then you will get phi dash Unj into del Unj del Wji, and this is very simple, right? Xni. So this is the one. Now, this part is delta Nk, right? This part is delta Nk, you replace the delta Nk, so W dash Kj this. Now, we just replace the whole thing as delta Nj. So this is delta Nj, it will be independent of K, right? Because K will be summing up here. So this one, so delta Nj Xni. See, Wgi plus eta into delta Nj Xni, you see here, the formula is same, right? W dash Kj del eta into delta Nk Vnj. Same as this, delta Nk for the output layer. This one is a bit simple, but this one will be a bit complex. And using the delta Nj, we can calculate delta, using delta Nk, we can calculate delta Nj. And we can go, if you have, say, further more hidden layers, so the same delta Nk will be used. Okay, so phi x is this. This is the activation function we call. Eta is the learning rate. Okay, there is another aspect of it. We are feeding one data point, and then we are modifying the W. Then again, we are feeding second data point. We are modifying W, third, modifying W. So after maybe 1000 data, if you have to train, maybe after 100 data points you fed, right? You may think that, okay, now 100 first data I'm feeding, that may spoil my earlier learning as well, right? Isn't it? It's like this. Say, you are first you are learning maybe addition, then subtraction, then multiplication, then division, right? Now, first, since I taught you, say, maybe addition, when I taught you subtraction, will you forget the first one? Right? No, in general, human being does not do that, but machine may do that. So whenever we are feeding one by one, you should not forget the impact of the first change. Okay. Suppose it is another thing. Normally, I give that example whenever I teach on board. Say, suppose I am teaching something, okay, and I am referring you to look at something this side. So you asked, right, that, sir, I cannot see whatever is there in your back. So can you please move a little bit? Now I move this side, right? So now you can see here. But there is someone sitting this side. That person may not see what is written here, right? So C complains. Then I try to adjust. So if I adjust and move here, then the complaint of the first person I cannot satisfy, right? So I have to remember the complaint of the first person as well. So I have to try to adjust, right? Because second person's complaint, to satisfy second person, I cannot just spoil the complaint of the first person. And that's why we introduce the momentum term whenever you are modifying the Wji, right? Now, this is the formula we have, Wji nth iteration for the nth data. which is equal to eta into delta wji. This is the modification, okay, we are doing. But there was another modification for the earlier data point as well, that is n minus 1. Don't forget that. Actually, here it would be delta of wgi n minus 1. And multiply that with a constant called alpha. Alpha value is comparatively, it is a higher. Eta value is very small. Alpha value is normally more than 0.6, 0.7, 0.8, 0.9. That means you give importance to the earlier modifications as well. And this alpha part is called the momentum. That means you are going towards an optimum value. Now, if someone complains, then don't spoil the earlier one. You try to adjust, but remembering the past modifications. Don't never forget the past things, whatever past steps there are. To remember that, we introduce the momentum. And this is delta wji. Yeah? You do the current modification, the contribution of the current data point, but don't forget the contribution of the earlier data point as well. So we add that one, and that is the called the this particular constant. The eta is the learning rate, and this alpha is called the momentum. And value of momentum in general is high, okay, because you give more importance to the previous data. Now, another thing is that number of training samples, as we said, okay, you increase the number of training samples, okay, you can introduce more number of data and you will get better result, okay. But here it is number of weights is W, error is whatever error you want to achieve, n by epsilon error, order of that, right? So if the, number of parameters is 10 and epsilon is 0.1, so it is expected that your number of training sample will be 100. Okay, that is the 10 times of this one. Okay, so that is the normal concept or what shall I say, that practical examples we have seen. So I'll stop sharing this and then I'll come back here and try to take your questions. Okay? And the same neural network we will be using in the deep neural network model or deep learning. Sumit, do you have any question?
Hello?
Yes.
Sir, can you hear me?
Yes, tell me.
Sir, I have a question.
Yeah.
This is with respect to the choosing the inputs. You told like the input, normally it is the characteristics of something which we want to measure. Suppose, there are some characteristics, similar characteristics.
Mm-hmm.
Okay, how to choose you know a single I don't know how to put it in financial data. We
Mm-hmm.
have like lot of ratios which measure the same thing. Okay, so how to choose one characteristic, or is there a method to choose the input characteristic which gives a good classification?
Yeah, good question. Actually, for neural network, if you have say 100 characteristics characterizing the object, and if you know that some of them, maybe source of some of the characteristics are common, right? That's what you are trying to say.
Yes, yes, yes.
And so they maybe say there is some high correlation, actually we call between the features.
Yes.
In NN, actually you can feed all, does not matter. Machine will
Okay.
take care. But one thing is only there is an issue that it will increase the complexity of the network. You understand, right? And maybe, yeah. But in NN, you do not need to bother about that. Now, if you want to reduce the complexity of that, there is another topic in machine learning or in pattern recognition called feature selection. Okay, now that is a different, there are a lot of lot of techniques available where you can select the important features for your problem or relevant features to solve the problem. Okay, so I suggest you to read the feature selection technique. One is that you just see the correlation between the features. If there is high correlation, you can get rid of one feature. You do not need to consider that one. There is another feature selection technique, very popular one called PCA. There is another one called ICA, principal component analysis, independent component analysis. Okay, so you can do that. You can reduce features, and so that whatever you are saying, there is a very bad idea to feed the correlated data, right? You are right. But in neural network, it will not harm you. Only thing is that the computation will be higher. That's it. Don't worry. You
Oh,
just feed all that.
oh, okay, sir.
Excuse me, sir.
Yes, yes. Tell me.
Sir, I have a doubt from gradient descent.
What?
Actually, you said that for finding the global optimum,
Yes,
we have to change the W0 for finding the global optimum. Means if there is more than one local optimum. So,
yes.
is there any other technique of doing that, or we have to we should train the data sets again and again for finding it?
Uh, Actually, Sumit, what I have seen, in fact, I have noted, I have read actually, that if you just do stochastic gradient descent, which I said, right, you feed data one by one, it
Yes,
will
sir.
it can overcome the small global minima. There maybe say data is something like this, like stock market. Then the small global minima can be taken care of by this gradient descent. But
Okay, sir.
right now, I cannot remember other than that the multiple times or initializing multiple times and executing your program multiple times, there is any other way to avoid this local minima problem.
But sir, there may be chances to not get the global optimum.
Yes, yes, there is a chance. But there is actually, Swarup knows about this. You can give a search about SK Pal and Dinobandhu Bhandari, selection of optimum set of weights using genetic algorithm. So we have come up with with a paper. We have used genetic algorithm to find the optimum set of weights.
Okay, sir.
You can give a
Thank you,
search,
sir.
information science, sometime in 1992 or 94 it has been published.
Sure, sir.
There
I
is
think
another
some work. I think some work they do with multiple local minima, and then try to find a minimum of the minimum. So I think that is also somewhere there. They start it with different points to go to different local minima, and then out of that minima, they try to find out which one is the minimum.
Yeah, that's what I said, right? That you just execute your program multiple times and see that which one is the minimum.
Yes, sir.
Yeah, you are
And
right.
regarding that correlated data, I think that can be done like first they can apply clustering, okay, some form of clustering, because the clustering means there are going to be different groupings of similar data, and from there they can choose a sample or representative to train them, so that it will minimize
Clustering of features you are talking about.
clustering of features, right?
Oh,
So
okay.
features, so that the correlated features can be avoided. I mean.
Yes, that's what I said, that you find the correlation between the features and then you get rid of some of the correlated features. Yes, yes, yes.
So one more thing, like whatever we have studied, it's fine. Like how we have calculated the weight, how we'll propagate that weight is fine. But I would like to know how actually it is happening. How this
Oh,
hidden layer actually creating that I mean that system, the
yes.
linear boundaries to non-linear
Yes,
problems.
yes. No, good that you brought that point. I had in mind to explain that, but somehow I missed it. Maybe because since I'm talking separately alone and or something, people are not around. Okay. First thing, let me tell you how people view it. Huh? What people consider that when you are feeding the information in the input layer, and those information is passed to the subsequent layers, right? Nodes in the subsequent layer. what it is doing is that it is considering the low level information to some high level information. It is trying to consolidate the low level features to generate or to extract a high level feature. That is the weighted sum and giving the what shall I say, that nonlinear transformation, right? And that nonlinear transformation V and J, which is the output of the hidden layer, that is actually nothing but a high level feature constructed out of the low level input features. You can view that way. So instead of having, say, D features in the input layer, in the output layer, we are consolidating and generating or extracting some new high level features in the hidden layer. Then if we have, say, multiple hidden layers, we will do the same. When we discuss the CNN, the convolution neural network,
right. So it's extracting the higher level features.
Yeah, very good that you brought this point. So that's how it does. Okay, so instead,
once I heard that, I may be wrong. Once I heard that, if let us assume if I have a nonlinear problem data, then I cannot separate it definitely with a single line. So now what I can do, I can have a polygon kind of thing, the collection of multiple straight line. So that each straight line can be defined by a hidden layer. Is it something like that?
yeah, actually, I was about to tell that this is the first way to perceive how neural network works. The first one I said. The second one is I was about to tell the same thing, whatever you are trying to refer. Yes, thank you. So the second way to think about it, suppose you have some nonlinear boundary, right? Now it is just maybe a curve, right? Now if you have as a circle, and neural network always generates lines. That means whenever you are taking the inputs and sum them up and then getting the output, you are getting a line. Okay. Now how can we replace a circle by lines? So in the hidden layer, if you have, say, h number of nodes, you are generating h lines. Suppose h equal to 4. So but your nonlinear boundary is a circle. So you try to replace that circle by 4 lines. Maybe it will be a square. Okay. Now, if that square does not give you good result, then you increase the number of nodes in the hidden layer. So you will get maybe a hexagon or maybe heptagon, okay, octagon, and they will be close to the circle, right? So number of nodes in the hidden layer will be equal to the number of line segments in estimating or in approximating the circle, the curved line. Actually, I was about to tell that there is one very famous theory in mathematics that any curve can be approximated by line segments. Okay, Weierstrass theorem. You can give a search, Weierstrass theorems, and if you actually this Stone-Weierstrass theorem, Stone, you give a search, and Weierstrass, Weierstrass theorem. Weierstrass is a very famous mathematician, and what he has shown that if you have something, a curve, that can be always approximated by number of line segments. Now, if you have more number of line segments, you will be very close to the curve. If you have, say, if you try to approximate a circle by a square, right? Obviously, the error will be more. Now, instead of square, you approximate the circle by maybe a hexagon, right? You will be close to that. Then you approximate that by octagon. You understand the number of line segments you increase, you will go very close to the curve. And that is called Stone-Weierstrass theorem. So that is another way to feel it or perceive how neural network works. That means The first point, what I said, you can think of that in neural network, the hidden layers try to generate high-level features to classify the objects. Another way to be that if there is a nonlinear boundary separating the classes, you are generating number of line segments, right, in the hidden layer, and then you are approximating the curve using the line segments. Okay, the two ways to perceive it. Whatever is you convenient, you think about it. Stone-Weierstrass theorem. You can give a search and get it.
And now, like it may be you may, I mean, again, you'll cover it in DNN, I think.
Yes.
But
Yes.
let me put it here only. Like if single layer is sufficient, then why you need more multiple hidden layer? So just to get more abstract information from there or higher level information?
Exactly. Because say when you try to work on say face recognition and all those things, okay. Say if you have say some complex features, how many or you may not know, right? That how many pixel will constitute a particular feature. Say maybe you are trying to find out whether there is a contour, right? Or maybe a contour comprising of maybe 100 pixels, right? So you may not be able to consolidate those information in one hidden layer. That's why you need to go for the multiple layers. And you'll be surprised to know people are using now more than 500 hidden layers nowadays in CNN. But there is another reason in CNN as well, right? Because if you use MLP, yes, one hidden layer is sufficient, I can tell you. But we do not use MLP in deep learning, right? There are a lot of other issues because number of parameters will be so huge, you cannot just train in limited time. Because depending on the problem, if you have say number of input features are limited, you can go for MLP and just do that and execute that with one single layer, hidden layer. But if you have say millions of nodes in the inputs, right, like a face, if you feed an image 1024 by 1024, right, it is really difficult or very challenging to manage that type of those many nodes, right? It would be a huge number of parameters. Normally, we do not need that. then instead of doing that, if you just use kernels, filters, or maybe 100 filters in 500 layers, it would be cheaper. We'll try to explain that when we study CNN.
So that is the reason. I mean, like that actually message to everyone whosoever is present here. Like it should not be like blind, like going to like I have to use deep learning or I have to use CNN. If your problem demands, then only you should go. Otherwise, a simple MLP is sufficient. Your problem is like that. This MLP can do. Why should I go for some more higher level DNN and CN?
Exactly. Even if KNN works, right? Why shall I, if CNN works, KNN, right? K nearest neighbor works. Why shall I go for ANN?
Exactly. No simple. Why should I go? It depends on the problem.
Exactly.
So anyone having any more questions, then you can ask, please.
Yeah, please. Okay. Then another
hello, sir.
point.
Hello.
Yeah, or go tell me.
Yeah, actually, these lectures are so nice. It would be very great to have these recorded videos at least for a short period of time so that we can,
No,
review.
it's not short period. We are actually editing some of the parts, extra thing.
Okay.
We have our own YouTube channel that is called Netra Lab, and
Okay.
very soon to share the link. Don't worry.
Okay, thank you so much. Yes. Okay. And sir, yesterday's that printed that PDF presentation, I think you have not shared. The handwritten one was sent.
No,
Okay.
I think
Sarup, have you
I think it has. Sumit, whether you have got that PDF or not, I think you have shared. Am I right, Sumit?
Yes, sir. I have shared in the group, WhatsApp group.
So I think it's there. All the PPT as well as the handwritten notes are also there in the group. If not, then we can share it. Don't worry.
Okay, thank you. Thanks.
Okay, I will resend it.
Okay, another thing I just want to mention that initially our plan, right, was to discuss deep neural network on the fourth day. But instead, what I decided that it is better since we are going for this technique, right? Then I'll finish SVM tomorrow, and then on the last day we will discuss about deep learning. I hope that is not an issue for you guys because it would be easy for you. Yeah, it would be convenient for you also.
Achha, now just tell me all the participants, when should we conduct the examination? Because I was expecting to do it on Thursday. So is it possible to do it on Thursday? Hello, can we able to appear for that exam tomorrow? Whatsoever we have discussed today, till today? Or otherwise we have to do it after completion of that that whole session after Friday. I think we have to do it so that entire course, and we can conduct it around next week, somewhere in between, and then after that with that percentage we'll share you the e-copy of the certificates. I think that will be better. Then you can have a knowledge of entire session, all the 5 day session.
Yes, sir, I agree. After the session is complete, we
Yeah,
can
fine.
do the exam.
So
Yes, sir.
that will be better. So next week
Yes.
we will announce in the group, and then one day fully you can prepare and you can just appear for the examination.
Yes, sir.
So anything having any questions? Then we'll wind up today.
Yeah.
It's already 1 o'clock.
No questions, sir.
Okay. Okay. See you tomorrow.
Thank you so much. Thank you, Dinamita.
Thank you, sir.
Thank you, sir.
Tomorrow.
Thank you, sir.
Bye.
Okay.